Hi, welcome to Chemical Formulas Review Part 1. Today in this review we are going to look at the element versus the compound, talk about what specifically is a chemical formula, look at different types of formulas, talk about oxidation numbers and the rules for assigning oxidation numbers, how to determine oxidation numbers, and finally phase abbreviations when we look at them in terms of chemical formulas. Alright, so let's start out by talking about an element versus a compound. And this goes back to a little bit with atomic structure and periodic table and bonding. So now we're bringing these two concepts into the world of chemical formulas. So what is an element? Well, an element is going to be composed of one type of atom. And the example we have right here is titanium. And again, this is from periodictable.com. And an element cannot be broken down. It cannot be broken down into a simpler substance using chemical means. So in other words, we can't, if we tried to burn an element or something like that, it's not going to break down any farther than what it already is. You can't really break apart the atoms that compose the element into a different substance by using chemical methods. Now let's look at what is a compound. A compound is defined as a pure substance composed of two or more different elements that are chemically combined in a fixed proportion. Here we have some nickel 2 chlorides. We can look at that. So if I looked at nickel 2 chloride, I'd say, well, there's a nickel, so Ni, and it's got a Roman numeral number 2, so Ni plus 2, and the chloride ion is Cl minus 1. So if I cross those down, I'd say this is NiCl2. So NiCl2, and remember we went over this in terms of ionic bonding because nickel is a metal, chlorine is a nonmetal, and this is how they would come together. And we know this is in a fixed ratio because there's a 1:2 ratio here based on the subscripts that are listed here. Another thing to look at is the fact that in nickel 2 chloride they are different elements coming together. So that is our definition of a compound. Two or more different elements that are chemically combined in a fixed proportion. Now what is a chemical formula? What does a chemical formula do for us? Well, it's going to tell us the number and the kind of atoms in a compound. Here we have two compounds. I have glucose and I have lithium sulfate. So if I look at the chemical formula for glucose, it's C6H12O6. So that's telling me that it's composed of three different elements. It's composed of carbon, hydrogen, and oxygen. And the subscripted numbers right here tell me the mole ratio of atoms that make up this particular compound. So in this formula for glucose, I would need 6 carbon atoms, 12 hydrogen atoms, and I would need 6 oxygen atoms in order to take those atoms with those numbers and put them together in some type of structure. If I look at lithium sulfate, which is Li2SO4, this particular compound is made up of lithium atoms, sulfur atoms, and oxygen. And again, the subscript is going to tell me how many of those particular atoms I need to make that particular compound. So there's 2 atoms of lithium, so I'm going to put a 2 here. There is an assumed 1 right here by this sulfur atom, an assumed 1, so 1 sulfur, and 4 oxygen atoms. So if we said, well, what's the ratio of this? We'd say, well, it's a 2:1:4 ratio that makes up this chemical compound. So again, a chemical formula is going to tell you the type of elements involved and the number of those elements needed to make that particular compound. Now let's look at two different types of chemical formulas. There's a more specific one called a molecular formula. Remember, when you see the word molecular, we think molecules. Molecules. And if we think molecules, we're thinking covalent bonds. Covalent bonds. And if we're thinking that, we're thinking non-metals. Non-metals. So if you see the molecular formula, that's a more specific formula that applies to the kind and number of elements in a molecule. So these are molecules, and they're only going to contain non-metals. So a molecular formula specifically looks at those formulas, those compounds, that only have non-metals involved. Here's 2 examples: sulfur dioxide, SO2, and tetraphosphorus decoxide. And we'll go over later in future videos how to actually name these. So both of these would be considered molecular formulas because they are made of nonmetals and they are held together by covalent bonds. Then we have the empirical formula. The empirical formula is defined as the simplest atom ratio in a compound. It can't be simplified any farther and in the same ratio as a molecular formula. So let's look at the formula for caffeine is C8H10N4O2. To figure out the empirical formula for this, I want to look at each of these numbers and see what number will divide into all of them at the same time. So I could say, well, 8, 10, 4, and 2, those are all even numbers. So this can be divided by 2, this can be divided by 2, this can be divided by 2, and 2, of course, can be divided by itself. So the empirical formula for this would be C4H5N2O. And then we have a 1 there, but it's assumed 1, so we don't have to put it in. So if we said, well, what's the ratio here? We'd say it's 4 to 5 to 2 to 1. So this is the empirical formula of this molecular formula for caffeine. When we talk about oxidation numbers, these are the numbers that are used in chemical bonding. So let's talk about the rules for assigning oxidation numbers. And remember, on your periodic table, these are selected oxidation numbers, selected oxidation states. So there could be more for a particular element, but in terms of New York State, these are the ones that they're telling you that you need to be familiar with. So the first rule that you need to know is that the oxidation number of every atom in a free element is 0. So in other words, if I said to you, well, what's the oxidation number of pure carbon? Well, carbon by itself would be 0, or sodium by itself, 0. This also applies to the diatomics. Diatomics are considered free elements, so they'd also be 0. In a compound, the algebraic sum, meaning adding together, of the oxidation numbers must be 0 since all compounds are electrically neutral. I'll show you how this works in a second when we do a couple of examples. The oxidation number of an ion is the charge on that ion. So if I say to you, hey, I have a fluorine ion, and you know fluorine has a charge of -1, well, the charge of fluorine is -1, therefore the oxidation number is -1. In a polyatomic ion, the sum of the oxidation numbers of its component atoms must equal the net charge on the ion. So again, we'll look at this a little bit when we do some examples in a second, but if I took the polyatomic sulfate, for example, SO4-2, then that whole ion, if I was to figure out the charge on sulfur and oxygen, and I put them together looking at the number of elements involved in the polyatomic, they would have to equal an overall charge of -2 and not 0. In most compounds, hydrogen has an oxidation number of +1, but be really careful here. If you look at your periodic table, you'll know that hydrogen has a charge of +1 and -1. So what you want to watch out for is situations called metal hydrides. Metal hydrides. Beware the metal hydrides. So an example of a metal hydride could be something like NaH, sodium hydride, where we know that sodium has a charge of +1, therefore the hydrogen has to have a charge of -1. Or if we had a situation like calcium hydride, so CaH2, calcium can only be +2, and if I'm going to make this electrically neutral, I need 2 hydrogen atoms involved in this ionic compound, so hydrogen has to be -1. 99.9% of the time for hydrogen, you're going to be +1. Just be aware of the metal hydrides. And finally, in most compounds, oxygen has an oxidation number of -2. Yes, you can have a peroxide, and in AP chemistry, you might even encounter a superoxide, but for the most part, for oxygen, the charge is going to be -2. Now let's look at some examples of assigning oxidation numbers, and we'll start easy and then we'll get to a little bit more complicated ones as we go through. So the way that I teach my students how to assign oxidation numbers is that when I look at the chemical formula, I say to them, you know, tell me what the number of each atom involved is by looking at your periodic table. So they look at calcium and they'd say, well, calcium's +2. In chlorine, because if this is positive, this has to be negative because we're dealing with an ionic compound. Chlorine has to be -1, and they know that the whole compound is electrically neutral, so it's going to equal 0. There is an assumed 1 right here, so I tell them to just multiply down. So 2 times 1 gives me +2, and -1 times 2 gives me -2. So +2 and -2 gives me 0. So therefore the oxidation numbers for the elements involved in this compound would be +2 and -1. Always write the originals, not after they're multiplied times the subscripts. Always write what is coming off your reference table. Let's look at this one right here. This is sodium carbonate. Now sodium only has one charge associated with that, and that is +1. So I'm going to write that over the top. Carbon's a little dicey. There's multiple oxidation states for carbon, so I'm going to leave that alone for right now. And I'm going to go with the assumption here that oxygen is going to be -2. So I'm going to write a -2 over the top here. So -2 times 3 gives me -6. This whole thing is going to equal 0. 1 times 2 gives me +2. So now the question is, well, what number right here, if all these numbers are added together, what number here will give me an overall charge of 0? And the answer to this one would be +4. So carbon here is +4. And again, I'd go to my reference table and I double check to make sure that that charge actually exists, and then I'd move on. Now let's look at this one here. This is magnesium hydroxide, and this has a bracket, and we think of a distributed property when we have brackets, so we have to pay really close attention here. Magnesium has an overall charge of +2. Oxygen I know is -2, and hydrogen is +1. So now I just want to double check to make sure that the algebraic sum, if I add these all together, is 0. So we know that there's an assumed 1 here, here, and here inside of the parentheses. So 2 times 1 gives me +2. And then really this 2 distributes across. Instead of having a 1 here, really this is a 2, and this hydrogen is 2. So -2 times 2 gives me -4, and 1 times 2 gives me +2. So again, the whole thing is electrically neutral. That is the distributed property with parentheses. So be really careful there that you make sure that you know how to do that. Okay, let's talk about this formula. Cu2SO4. Okay, what I know that oxygen is going to be -2, and -2 times 4 is going to give me -8. Okay. Now the issue with this particular problem is that I have copper here, and copper is a transition metal that has multiple oxidation states, specifically +1 and +2. So I need to figure out which one I'm going to use. And sulfur also has multiple oxidation states, so I need to figure out which one of those I have to use. So the way that I'm going to do this is I'm going to break this apart into its positive ion and its negative ion, specifically looking at its negative ion, which is the SO4. If I look on reference table E, I know that SO4 has an overall charge of -2. So if SO4 has an overall charge of -2, that means this copper has to negate that -2. If I put a +2 up here, well, +2 times 2 gives me +4. That's not going to work out. But +1 times 2 is going to give me +2. And that +2 right there and that -2 right here are going to cancel each other out. So I am assuming, and I'm going to double check myself here, that the charge on this particular copper is going to be +1. So okay, so +1 times 2 gives me +2. -2 times 4 gives me -8. That means this sulfur right here, to keep this whole thing electrically neutral, has to be +6. +6. Because 2 plus 6 gives me 8, -8 gives me 0. So this is going to be +6. And again, when you do these, you always want to go back to your original oxidation numbers if they're saying, well, what's the oxidation number for this particular element? So be careful about that. Let's look at our last one here. And this is one of the, at least from my students, this is one of the most nasty problems to assign oxidation numbers to. But if you do this little trick, it's not that bad. So this is ammonium hydroxide. And ammonium hydroxide is composed of 2 polyatomic ions. So what I tell my students to do is break these polyatomic ions apart. You know that NH4 is +1. And you know hydroxide is OH -1. So what you want to do here is assign oxidation numbers based on the charges of these polyatomics. So if I look at the hydroxide, okay, I know that oxygen is -2. I know that hydrogen is +1. So -2 plus 1 gives me an overall charge of -1. And that's really what I want right here. I want these two to match. Now, let's go to the ammonium because that's always a little bit dicier. Okay, hydrogen always has to be +1 unless it's with a group 1 or a group 2 metal, on occasion one of the poor metals or transition metals. But most commonly when we see these metal hydrides, it's usually with group 1 or group 2. So in this case, because nitrogen's a nonmetal, hydrogen here is going to be +1. So 1 times 4 gives me +4. The overall charge on this is +1, which means nitrogen has to be -3. -3. Now, it's not all that common that we have a negative ion first and then the positive ion second, even though these are parent charges because it's a covalent compound, but we're used to seeing positive and then negative. Get over it. With the ammonium ion, it just doesn't work that way. So the nitrogen is going to be -3, the hydrogen is going to be +1. This is a polyatomic. It's going to have an overall charge of +1. So if I had to go back here and assign original oxidation numbers, I'd say my nitrogen is -3, my hydrogen is +1, my oxygen is -2, and my hydrogen over here is +1. And again, the easiest way to do this is to break it down into the two polyatomics. Phase abbreviations. Basically, this is when you're looking at a formula and you're trying to figure out what state it's in. So is it a solid, a liquid, a gas, or is it aqueous? So a little s in parentheses is going to be a solid, just like this solid potassium permanganate right here. For a liquid, it's going to be a lowercase l, or in some cases, in parentheses, it's going to be a cursive L, like so. And I have some liquid gold right here to showcase that. For a gas, I have something known as chloropicrin. In World War I, the Germans used chloropicrin as sort of like a tear gas type of thing. It would make the soldiers throw up, and then they'd have to take off their gas masks, and then they would get exposed to even nastier stuff. In the United States now, at lower concentrations, safe concentrations according to the FDA, this is actually used in agriculture. But at higher concentrations, not so fun. So that's my example of a gas. And finally, aqueous. And this is the most important one to understand. So aqueous is represented by the letters AQ. What this means is that something is dissolved in water. So dissolved in water, which ultimately means you're going to have some type of mixture. So KMNO4 as a solid would be KMNO4 with a little s right there. KMNO4 as a solid. Pretty ionic compound, purple, interesting stuff. As an aqueous solution, here is my KMNO4 aqueous, AQ. That means the potassium permanganate has been dissolved in water, and we see that purple hue all the way through the solution. This is a mixture. I could separate this mixture out by evaporating out all the water. So if you see something defined as aqueous, that means you have something dissolved in water. So what did we learn? Well, we talked about the difference between an element and a compound. We went over the definition of a chemical formula. We talked about some different types of formulas, like a molecular formula and an empirical formula. We talked a little bit about oxidation numbers and the rules for assigning oxidation numbers. Then we did some examples where we actually went through and determined some oxidation numbers. And finally, we talked about phase abbreviations like solids, liquids, gases, and aqueous. If you need more help, feel free to contact me. I'm always looking for feedback. Hope you have a great day.